Let's investigate a violation of Bell's inequality, which Alice and Bob can use to verify that their Einstein-Podolsky-Rosen pairs have not been measured in transit by an eavesdropper. In this video, we will focus on the Clauser, Horne, Shimony, Holt inequality. We can abbreviate this name as the QKD inequality. Alice and Bob are going to perform measurements on qubits that they receive from an EPR source. An EPR source prepares EPR pairs. These are Einstein-Podolsky-Rosen pairs. We can imagine pairs of qubits that are prepared in a Bell state that is specified by two classical bits, zeta and xi. We're going to fix the values of zeta and xi. So that means this EPR source is preparing the qubits in the same Bell state. So let's consider the following experiment, which needs to be performed repeatedly. We need many trials of this experiment. We have an EPR source that prepares two qubits in a maximally entangled Bell state. Then we have a mechanism for distributing the two qubits to Alice and Bob. So Alice gets one of the qubits and Bob gets the other qubit. Alice and Bob then need to make random choices. Alice chooses between two observables, A0 and A1. Bob also needs to make a random choice, and Bob will choose between two observables, B0 and B1. So once they make their random decision, they will perform a measurement on the qubit that they have received from the EPR source. The outcome of this measurement will be either +1 or -1. Plus or -1 are the eigenvalues of these four observables. So these are the possible outcomes for Alice and Bob's measurements. Now we need many trials of this experiment. We need many trials so that we can compute expectation values. So we're going to consider four cases. These are A0B0, A0B1, A1B0, A1B1. So these four cases correspond to random choices made by Alice and Bob. Let's pay close attention to this term over here. This corresponds to Alice randomly choosing A1 and Bob randomly choosing B1, and then performing a measurement, and then we want to compute the expectation value. But keep in mind that there is a minus sign in this definition. So we're going to consider these four expectation values. This is the notation for an expectation value. We're going to take the expectation value of these four terms. And we're going to have plus signs for these three terms and then a minus sign for this term. Now this is very important. This quantity is going to be used to define the QHSH inequality. First, before we analyze the QHSH inequality, let's consider these particular choices for Alice and Bob's observables. So these are not the only choices that can be made, but for this video, we're going to define the observables with these expressions. So let's start with Alice's observables. A0 is defined as Pauli Z multiplied by -1 to the power of a classical bit, eta. A1 is defined as Pauli X. Now this classical bit eta is very important. It allows us to classify the four Bell states into two groups. So let's consider the Bell states that have zeta and xi equal to each other. So this is either the 0,0 or the 1,1 Bell state. So we can describe this as beta 0,0 or beta 1,1. So this means that zeta and xi have the same value. Now in that case, we're going to set eta equal to 0, and that will deactivate this minus sign. So that means the definition of A0 is just Pauli Z. So this is just like when we described entanglement-based quantum key distribution in the previous video. So Alice and Bob both made a random choice between measuring in the Pauli Z eigenbasis and the Pauli X eigenbasis. So in this case, Alice is randomly choosing between these two observables, Pauli Z and Pauli X. Let's consider the other case where eta is set equal to 1 and this minus sign is activated in this definition. So in that case, we're going to have A0 equal to minus Pauli Z. So that's when we set eta equal to 1. And that corresponds to the case where zeta and xi have opposite values. So that means that our EPR source is either preparing the beta 0,1 state or the beta 1,0 state. So if the EPR source is preparing a Bell state that is specified by different values of zeta and xi, then we need to set eta equal to 1 and activate this minus sign. So this is a very useful convention because this classical bit eta allows us to consider those two cases in a single expression. So down here, we can see eta appearing in these equations. And whenever eta is equal to 0, that corresponds to the EPR source preparing either the beta 0,0 or the beta 1,1 state. And when eta is set to 1, that corresponds to the EPR source preparing the beta 0,1 or the beta 1,0 state. So this is a very interesting convention that we're using. So we've just defined the observables for Alice. Let's also define the observables for Bob. So this expression actually defines two observables. K is also a classical bit. It can be either 0 or 1. B0 corresponds to K equals 0. So that deactivates this minus sign. B1 corresponds to K equals 1, and that activates this minus sign, and then we have a minus sign present in this definition. So observe that there is a normalization coefficient of 2 to the power of minus 1/2, which we can also write as 1 over the square root of 2. And then over here we have the sum of Pauli Z and Pauli X. So for B0, we have Pauli Z plus Pauli X, and for B1, we have Pauli Z minus Pauli X in the brackets over here. So we have just defined 4 observables. 2 of those observables are for Alice, and the other 2 are for Bob. Now we can use these 4 observables to define another more complicated observable. So keep in mind that these 4 observables, A0, A1, B0, and B1, they have eigenvalues of +1 and -1. So those are the results of the experiments that Alice and Bob will perform when they measure the qubit that they receive from the EPR source. But then we're also going to consider this combination of observables, and we're going to treat that as an observable. But this observable is not going to be measured in a single trial. It's not going to be measured in a single experiment. Instead, we're going to compute the expectation value of this observable by computing these 4 expectation values over many trials. So that's why we have defined this quantity over here. Observe that if you remove these expectation value signs, you can rearrange these 4 terms and you can condense it down into this expression. So over here you can still see the A0, B0 term. And over here we have A0, B1, A1, B0. And we also have the minus sign in front of the A1, B1 term. That's very important. That is the only one that has a minus sign in front. So now what we want to do is consider the maximum possible value that we can get for this expectation value. So these 4 expectation values combined in this way, they are equivalent to computing the expectation value of this observable down here. So let's consider what the maximum possible value for this expectation value is. First, let's consider the case where we can arbitrarily assign plus or minus 1 to these 4 terms. Now, if we assign +1, +1, +1, and -1 over here, we'll have a cancellation of signs, and that will give us +4. So we'll have +4 as the maximum value. But that is not allowed. We're not allowed to arbitrarily assign values to these expectation values. So let's consider the classical upper bound. So for a moment, let's forget that these are quantum mechanical observables. Let's treat them as classical observables, which have 2 outcomes, +1 or -1. And we'll focus on this expression down here. So let's imagine that we're dealing with classical observables, and let's imagine that we compute the expectation value. What is the maximum value that we can get? Let's suppose that B0 and B1 have the same outcome. So they're either both plus 1 or they're both minus 1. That means we're going to have plus or minus 2 as the result of this sum. And it also means that we're going to have a cancellation in this term. So that means this term will vanish if b0 and b1 have the same outcome. So this term vanishes, and over here we have plus or minus 2. Now let's consider another case where b0 and b1 have opposite outcomes. So it's either plus 1 minus 1 or minus 1 plus 1. If they have opposite values, then this term is going to be plus or minus 2, and this term is going to vanish. So the opposite values will cancel here, and this term will vanish. And then we'll have plus or minus 1 times plus or minus 2. So we can see in both of these cases, the maximum value we can get is 2, and the minimum value we can get is minus 2. So if we take the absolute value of the expectation value, then it has to be less than or equal to 2. 2 is the classical upper bound. So we've seen that if we can arbitrarily assign the values of these expectation values, we have a maximum value of 4. And classically, we've seen that the upper bound is 2. In quantum mechanics, the upper bound is in between these values. So it violates the classical upper bound. This is called a violation of Bell's inequality. We can consider the QKD inequality as a type of Bell inequality. So we have a violation, but it is not as extreme as going up to the value of 4. Instead, it is the value of 2 to the power of 3/2. We can also write this as 2 times the square root of 2, or we can write it as the square root of 8. What is really important is that this upper bound that we get from quantum mechanics is larger than the classical upper bound, which is 2. So this is what is meant by a Bell inequality violation. And this maximum upper bound has a special name. It is called the Tsirelson bound for the QKD inequality. This is the maximum value that quantum mechanics allows. And we can attain that maximum value for this expression if we use the maximally entangled Bell states. So if we have the absolute value of this expression over here, it has to be less than or equal to 2 times the square root of 2. Or we can write that as 2 to the power of 3/2. We're considering this as a positive value. Now, let's have a look at these expressions down here, which tell us the Tsirelson bound. So we're going to have plus or minus 2 times the square root of 2 appearing in these expressions. So these are just different ways of stating it. And these are general ways of stating it that work for all 4 of the Bell states. So first, let's rearrange this value, this observable, into this format by substituting these definitions. So over here, we're defining this observable in terms of these 4 observables. And if we substitute these definitions inside, then we can rearrange, we can get this expression. Let's see where that expression comes from. So if we substitute A0 and A1, over here, we're going to get Pauli Z with possibly a minus sign. And over here, for A1, we're going to get Pauli X. So that explains this Pauli Z and this Pauli X. But what about these sums and differences over here? So over here, we have B0 plus B1. Now, if we take the sum of B0 and B1, we're going to have a term where there is a plus Pauli X, and we're also going to have a minus Pauli X. So that means Pauli X will cancel. And we're just going to have 2 copies of Pauli Z. So we'll have Pauli Z appearing here. So the sum will give us Pauli Z. But there's also a coefficient. We'll have 2 times this coefficient of 2 to the minus 1/2. And if we simplify that, we'll get this coefficient 2 to the power of 1/2, which we can also write as the square root of 2. And we can factor that coefficient out. So that explains this ZZ term. Now let's have a look at this XX term. The XX term, so we've seen that A1 is Pauli X, and if we look at the difference of B0 and B1, we can see that this minus sign will cancel with the minus sign in B1. So if we take B0 minus B1, the Pauli Z terms will cancel, but the minus Pauli X will get another minus sign that will turn into plus Pauli X. So we'll have Pauli X plus Pauli X. So we'll have 2 times Pauli X, and then we again have this coefficient, and that gives us this coefficient when we simplify. So we have x, tensor product x. So you can see where this blue x is coming from. It's coming from the difference of b0 and b1. And we have that same coefficient. We have 2, and then we multiply by this coefficient, which is the same as 1 over the square root of 2. And that simplifies to the square root of 2 as the coefficient. So now we have this format, which may or may not have a minus sign depending on the value of eta. Now let's consider the observable in this format, and let's sandwich it between a bra version of this Bell state from the left and a ket version of the Bell state from the right. If we sandwich this to get the expectation value, we can bring in the bra and ket on this term and on this term. And then we can use this expression over here and this expression. We can substitute the results of evaluating those expectation values. So if we compute the expectation value of this ZZ term, when we have a Bell state, we're going to get minus 1 to the power of xi, where xi specifies which Bell state we're dealing with. And what about for this XX term? We're going to get minus 1 to the power of zeta. And that is this zeta over here, which specifies the Bell state. And if we substitute those values for the expectation value, we can also combine this minus 1 to the power of eta with minus 1 to the power of xi, and then we get minus 1 to the power of eta plus xi. And over here we get plus minus 1 to the power of zeta. So that comes from this expectation value of the XX term. So now we have a general way of writing this expression. So what we want to consider here is the case where both of these minus signs are deactivated at the same time, and the case where both of the minus signs are activated at the same time. So if we have minus 1, that will give us minus 2 times the square root of 2. So this is minus the Tsirelson bound. But if we have the case where both of them are deactivated, then we have plus 1, which gives us plus 2. Then we have plus 2 times the square root of 2, and that is plus the Tsirelson bound. So if we take the expectation value of this, then we're consistently going to get the Tsirelson bound. So it's very important to consider the case when eta is equal to 0 and the case where eta is equal to 1. So if eta is equal to 0, it vanishes over here, and then we're only interested in the states where zeta and xi have the same value. So we're either going to have 0, 0 or 1, 1 present over here. And if we activate eta, that means we have 1 over here. That means that zeta and xi have opposite values. And that is because of this 1 over here, we're still going to get either the Tsirelson bound or minus the Tsirelson bound. So that is the importance of including eta over here, because it allows us to generalize for all 4 of the Bell states. Now let's consider this final expression down here, and that's going to allow us to compute this expression, which actually gives us the same values. We're writing it in a different way, and that's going to give us a different insight. So this combination of observables can be written in this format, and we can also write it in terms of these ket-bra combinations. Now, why are we allowed to do that? It is because the Bell states are eigenstates of this observable. So we can write this in terms of the Bell basis. And this is a really fascinating relationship. So here we have a ket-bra formed from the Bell state beta 0 eta. And over here we have a ket-bra formed from the Bell state beta 1 eta bar. So this bar says you need to flip the value of eta. So let's consider the case where eta is equal to 0. Then we're going to have the beta 0, 0 state over here and the beta 1, 1 state over here with a minus sign. And what about the case where eta is equal to 1? Well, then we're going to have beta 0, 1 with this plus sign, and with the minus sign, we'll have beta 1, 0. So we're either going to have the case where both of the states have zeta and xi equal, or we're going to have the case where zeta and xi have different values. But what's really important is that one of the states that appear in this combination have the eigenvalue, which is the Tsirelson bound. And the other state, which is over here, that has the eigenvalue of minus the Tsirelson bound. And the remaining 2 Bell states that do not appear in a particular case of substituting the value eta, they both have the eigenvalue of 0. So that means this is equivalent to diagonalizing a matrix representation of this observable. So imagine we write this as a 4x4 matrix. We can diagonalize that matrix. That's the same as finding the eigenvectors and finding the eigenvalues. And then we can represent this in a different basis. We can represent it in its eigenbasis. And it turns out that the Bell basis is actually the eigenbasis for this observable. And the eigenvalues are the Tsirelson bound and minus the Tsirelson bound, as well as 0. So observe that there are only two Bell states that appear here in these Ketz-Bra combinations. The remaining Bell states that don't appear in a particular expression, they have the eigenvalue 0. So that's why they don't appear here. But the eigenstates that do appear in this expression, they have the absolute value of their eigenvalue equal to 2 to the power of 3/2. So that can also be written as 2 times the square root of 2, and it can be written as the square root of 8. So that is the Tsirelson bound. That is the maximum bound that is allowed by quantum mechanics. And if we perform the expectation value by sandwiching a bra, so we have a bra coming in from the left, and then we have a ket coming in from the right, and we sandwich these two terms, what are we going to get? Well, we're going to get these results over here. So you can see the Kronecker delta. So for this term over here, if we sandwich with a bra and a ket, then we need this 0 to be equal to zeta. So zeta has to have the value of 0. And we need xi to have the value of eta. And that's going to give us a non-zero value. But because these Bell states form an orthonormal basis, we're going to get 0 if these values don't match. So these will switch off if we don't have these values equal to each other. So this tells us that this term is only going to switch on if we have zeta equal to 0 and xi equal to eta. And what about for this term, which has a minus sign? We need zeta to equal 1, and we need xi to have the opposite value of eta. So that's going to happen for this combination over here. So we have these two Kronecker deltas multiplying. And the Kronecker deltas are only going to activate, they're only going to give us 1 if these two values are equal. So this allows us to write the same values that we have in this format. So in this format, we're activating these -1s with classical bits in the exponent. And over here, we're using Kronecker deltas to take care of the two cases. So if we set eta equal to 0, then over here we're going to have the 0, 0 state activated for the plus value. And if we set eta equal to 1, then we're going to have the 0, 1 value activated for this plus sign. And the other states are going to occur in this value over here. They're going to have minus the Tsirelson bound for their eigenvalue. So try and play with these expressions. Try and substitute different values for eta, zeta, and xi. And if you write it in this form and in this form, you're going to gain different insights. So you can express this observable in this format, and you can express it in this format. And then you can try sandwiching it between a bra and a ket. And you can see that you will get these values over here. So if we take the absolute value that is present over here of this quantity, then we're guaranteed to get the Tsirelson bound if the EPR source is giving us actual Bell states. But if there has been an eavesdropper measuring in transit, then we're not going to get this maximum violation of Bell's inequality. So we have a way of detecting the presence of an eavesdropper. So if we get a value that is less than the maximum value allowed by quantum mechanics, then we know that some of those EPR pairs have interacted with another system. So they are not maximally entangled.